All right, well, welcome everybody to the ninth session of Quick Pass. This one is the final. This is the final lesson where I introduce content, and this one here is not really content that it's just good to kind of keep in mind some things, but I think for the challenges and for the purposes of Quick Pass, um, it's it's not going to be as applicable. I mean, you can still use it, but it's good. It's good also to kind of realize some of these concepts we have when we're talking about computation. But if you remember last week, last session, session 8, we went over problem solving. I think that one really applies to solving some of these challenges and introduces some concepts for you that maybe you haven't thought about for when breaking a problem down. And thinking of those algorithms and those algorithmic thinking concepts, and that's it really is important to think that way because problems are going to be a lot like that. And just like Guillermo alluded to, there's four things that he's going to do his evaluation on to really kind of look at those core concepts, and that's messing with data structures. Those very basic data structures that we've been taught in this course, like lists and tuples, which are ordered collections. Then we have our unordered collections like dictionaries and sets, and getting good at changing data forms, taking data and changing another form, whether it be through a loop or through another process. Having mastery of those techniques at the very basic level will allow you to build something, and it may not be the most efficient and it may not be the cleanest algorithm, but having those four basic tools allows you to get the job done. And knowing how to use those tools is very important. And so, that lesson, it is good to think about and revisit. And then at the end, instead of exercises, because we stopped giving exercises because once you focus on those application requirements, the part 2, we've been going over like a Powerball generator, and we're going to continue that tonight after the lesson, so we can get more practice dealing with those primitive data types and those basic data structures and changing them around and looking at loops. And I think that's really important to help us exercise our computational thinking. So let me go ahead and start sharing my screen. I think this is it. Okay, just give me a thumbs up or let me know if you can see my screen. Good to go. Outstanding. So in this lesson, we're going to talk about algorithms, the complexity, and big O notation. Again, this one will be a shorter one. It's a lot of concepts that we really don't need to spend too much time on breaking down, but it does introduce some kind of different ways of thinking, and just to let you see some creative ways you can process data and find things. And sometimes you may be faced with these exact problems when you're actually on the job doing something for in a code base, and you're having to solve a very unique problem for somebody, whether you're a consultant doing software, or you're building something on your own, and you're trying to figure out the answers to some problems as you're building a more complex project. So anyway, learning how to analyze efficiency algorithms, it is crucial for any programmer, and especially crucial in a lot of those activities which involve lots of memory usage or things that just take a long time. And when I look at it, I really hadn't thought about these concepts until my most recent job, which I do. I'm trying to turn machine learning algorithms into APIs. And part of that process is, breaking apart the logic and putting into specific calls, so this API can control the machine learning logic, and then just seeing all the internal processes that happen. And on my work laptop, which is a fairly high-end machine, some of these algorithms take hours to run. So I'll run it and just have to kind of walk away or do something else, because it's just completely tanking my computer for hours on end, sometimes overnight. And just understanding how it's working and how you can fine tune it can be important. Sometimes you can't avoid it, especially with machine learning, because you're processing just gobs and gobs of data. But so we're going to take a look at big O notation, and we're going to look at some algorithms. And then, we're going to go through that, and then we're going to kind of stop and then start looking at that problem again. And, we'll just kind of revisit some of those concepts we've learned throughout this course. So, yeah, without further ado, let's go ahead and get started. So, algorithmic complexity refers to the efficiency of an algorithm in terms of time and space. So it just assesses how an algorithm is going to run, how long it's going to take, and also how much memory it's going to take. Because, both of those resources are finite to us. Our computer only has so much memory. Cloud computing resources, as infinite as they seem, are still finite because the more you use, the more you pay. And if you're using, gigabytes or terabytes of RAM in a computing cluster, Amazon will be happy to charge you for that time, and they charge a pretty penny if you do. But you could also have your own resources, but then you won't have as much, and you'll have to think about how you're going to fit your process in the resources that you have. So, striving for efficiency is the goal. You want to make sure that whatever you're building can run quickly and use as little memory as possible. And when you don't do that, while one or two algorithms may be slow, they may not affect your application as much, but as it grows and you have nothing but slow and inefficient algorithms, that builds up, and soon you may have to deal with, refactoring, or just unexpected costs. You may, you have done your cost analysis on your cloud computing resources and find that you keep overshooting what you were estimating and having to pay more. That's not good for business. So you'll want to make sure that you are writing the most efficient code possible, or if you're leading a team of developers, that they're following those processes. So the way we can measure algorithmic efficiency, and we can look at execution time, we can look at memory usage. There are Python libraries, and there's illustrations of it here in the lesson. But we have libraries to show like how much memory you're using based on what you're doing, and it just kind of highlights in the console exactly how many megabytes of memory you're using, or gigabytes, depending on what your functions are doing. Big O notation, that describes the upper bound of an algorithm's growth. You'll hear that a lot, big O notation. If you just Google big O notation, software development, something like that, you'll see a plethora of resources with all different types of descriptions, videos, animations. You'll find that, maybe you just need to learn FizzBuzz and big O notation and how it applies, and you should be able to get a job as a software engineer, because you'll see that it's a big part of like interviewing processes. Spoiler alert, I've never actually been asked about big O notation in my job interviews. I have been given, simple problems to solve, but they haven't been, like FizzBuzz or anything, but they do happen. And we have, I have asked a question very similar to FizzBuzz to somebody applying to, one of the companies I worked at. So, it's good to think about these things, and it's good to look them up. I actually have a resource. Hold on a second, I'll be right back. This book, Cracking the Coding Interview, is a pretty good one. I bought this just to kind of see what's involved. When I first graduated Platoon, and I'll put a link to it in the chat or into the Slack channel. This one has a good section on big O notation and how it works, and it has different languages too that you can look at. So but it provides a simplified way to compare algorithms' performance. And you can calculate it based on looking at different portions of your function. If you have nested loops, or if you have a simple addition operation, you can add those pieces together to come up with a formula that matches one of the ways we annotate big O notation, which typically is a big O with a number or some sort of like little algebraic formula in the parentheses. And so we have some examples of Python code snippets that kind of demonstrate those big O notations. What you're going to find is, some of these algorithms look weird. Some of them make sense, or completely straightforward, and it's pretty easy. And so for this first one, this which is O of 1, this is constant time, which means the execution time memory remains constant regardless of how big of an input you have. So you could have an input size of 1, or you can have an input size of 10 million. It doesn't matter how big it is, because what you're doing only involves a single action. And one of those, in this example here, we have our constant time function. And let's just do a little bit of revisit just so we understand how functions work, because functions are a key part of learning Python and understanding it and writing Python. Again, we have this keyword def, which is our keyword, tells Python we have a function name coming up. And then we have our name, constant time. And then we have these parentheses here. And in these parentheses, we actually do have a parameter. Some people call them arguments. So it looks like this one is a keyword for array. Array is another name for a list. And then you have the colon. And then if you look, we have our code is indented in. And then we have a return statement. So we're returning something back from the function, and we're returning something. It could be anything. In this case, we're actually referencing the array. So we're looking at an array or a list coming in, and we're identifying an index that we want to return. In this case, we want to return the first index. So it's a pretty simple function, but it doesn't matter if you look at how this works. It doesn't matter how big the array is. As long as you have the index, it's going to take the same amount of time whether you're pulling the first one, the 15th one, or the 10 millionth one. It doesn't matter. It's all going to take the same amount of time and computing resources to give you back the element in that list, because you're going straight to a location. It's like knowing the address, so you're going straight to it and you're getting it. You're not trying to search for it. You're not like, it's in one neighborhood, but you know exactly where the house is that you're trying to get to, or the business in this, group in this mall, for example. You know exactly where it is. You're going to get it. It's going to take the same amount of time to get to it, or a similar address that's the same distance away from you. It's all the same. So that's constant time. And it's O of 1. The next one is logarithmic time. So it's O log n, and that represents logarithmic time complexity, where the timer space consumption grows slowly as the input size increases. And so this one looks a little more scary, looks a little crazier, like what's going on here? And I think I put it over here on my VS Code window. I think it's the first one here. And so let's take a look at this function and see how what it has, and kind of think about all these components so we can read it, because it does look scary. So we have here our def keyword again. We have the name, so it's called binary search. And then we have a sorted list. So we're calling this first argument sorted list, and the second argument called a target. And and you can take a look. So when we see this, we know, okay, this is probably a list coming in. And then this is, probably going to be a single item in the list, but we don't know what it is yet, but it's a target. If we look at the example down here, this function call, we have our list of 1 through 9, and then our target's a single integer. So okay, so we're looking for an integer. In this case, we're actually looking to return an index. Oh, I got something. So if we look at this here, we start looking at the logic under the function call, it looks like so it says left comma right equals, and then we have a 0, and then the length of our sorted list and -1. And so we're saying left and right. What could that mean? What does this mean? Does anybody have any idea what this means to them? How we're looking at this? Nika says left and right of list. So yeah, the left side looks like 0. So that would probably indicate, an index. And then the right is, the length -1. That makes sense because you want the length is going to be, if you have a list of 6 items, right? Well, the 0 is the first item, but 5 is the last index. So if we're looking at indexes, we have to take the length and then subtract 1 to get the indexes. So we're saying left and right are that. And then it's while left is less than right. So if 0 is less than whatever the length is of a list, well, that's gonna evaluate to true, most likely. So we're gonna enter a while loop. So we have a while loop here, and we know that while loops run as long as this evaluates to true. So we have to think about what left and right, what they mutate to as we're going through each iteration of this list. So inside the loop, we can assume it's going to evaluate to true if we have any kind of list that's greater than 0 length. So we specify a new variable. So it looks like we're getting into a variable assignment, and we're calling mid or middle, and we're saying, well, we want to do a quick mathematical operation. And in Python, I think I covered this. It covers the PEMDAS, the order of operations. So parentheses, of course, come first with that. So anything inside of parentheses gets done first. So we're adding left and right, and then we're doing the floor division, so that double slash by 2. What that's going to do is get us the closest number and ignore the remainder in case it's not a nice even division. So it kind of forces a even division, if you will, and gets us the middle, the closest to the middle that we can, based on how big our list is. And then it looks like we're accessing. So does anybody remember what this means? So we have a sorted list, and we have these square brackets with some sort of variable in here. What are we doing here? Yep, we're indexing, right? Based on whatever this result is. Yep, so we're saying, hey, and really we're taking a first stab. We're like, hey, if the one we're picking equals our target, return. So we're going to end the function and return that because we found the index of whatever we're looking for, okay? Most likely that's not going to be the case, but it's good to go ahead and do that because we may hit it spot on. So if that doesn't happen, if this evaluates to false, we'll go to this next, and we have an elif or else if statement here. And so if this one evaluates to false, we're going to move down to this next one here, and we're going to say, okay, well, if sorted list at the index of mid is still less than the target, then we're going to say the left side of the list now equals mid plus 1 because we don't want to look at anything else below that. So what we're essentially doing is splitting this list in half. And it's a very efficient way to look at something, right? So it's the same way as if like you're going into a dictionary and you have a word, but let's say you have zero idea how to look at a dictionary and just think about, the letters in order and stuff. You just know that there's an alphabet, but you really don't want to even try and guesstimate where it is. So like your word starts with a W, right? The most efficient way, or finding a number in the closest number to what I'm thinking, right? So let's say I'm thinking of a number and between 1 and 100, and you want to guess the number. What's the most efficient way to start finding my number? Go right down the middle. And I can tell you if it's either if my number's higher or lower. And so you start off and say 50. I'm like, well, my number's 75, so my number's higher. And you say, cool. Well, I'm now going to discount 49 and everything else, or 50 actually, and everything else, because I know that now the number is somewhere between 51 and 100. I think you're going to guess 75 and be like, yep, you got it. And so that's exactly what this is doing. So it's taking the list and it's going to go ahead and reassign left to mid plus 1. And then if that's the case, it's going to go back up and run this loop again. So while left is less than or equal to right, which it should still be because it's not at the end of the list, it's going to do a calculation and move that middle point up to the middle of the new list or the split list. And it's going to keep doing that, and if it goes too high, it's going to go the other way and say right is now down and just forget about the right side. And so it's just a way to sort through, and eventually it'll hit this or hit nothing. So in that case, it's going to be a -1, and it won't be in your list. The time complexity of this is logarithmic, which means it grows slowly as the input size increases. So if you think about it, if you had a list of 10 items, right? It could do a maximum of 1, 2, 3, about 4 split operations, 4 or 5 split operations before it's going to find the number. But as that list grows in size to 100 or 1,000 or 10 million, right? While your first operation is going to knock off half of whatever that number is, it still has to split, further split down that list. And it may take a little longer than normal, or not normal, just a little longer than your constant time. And that's where it just shows like a slight increase of time based on how big your initial data size gets. Any questions on that or this like algorithm for representing logarithmic time? You're still confused on line 4. So this one right here, this while loop.
Sorry, I did not understand the explanation for line 3, and so line 4.
Right here.
Sorry. Yes.
Okay, so this right here is just setting the bounds of the initial list. So depending on how big your list is, it's just getting you the whole list to take a look at, so it can then find the middle. And so you're never going to hit this except for one time, and that's going to be in the very beginning of the function, because once it enters the while loop, it will never go back up to here. It'll always just stay in the while loop. So here it's just giving you 0 and the end of the list. And so then it's going to then do the calculation to find the middle, and then do the three if, else if, or else statements. Most likely to hit the first or the second option there. So line 6 or line 8, or it could hit line 10 if your number is actually higher than the target. But what's going to happen after it hits line 4? It's going to do this Boolean check, right? So a while loop, remember, only runs if this statement evaluates to true. So it's
You can set variables like that, like left and then comma right, and so it's saying that left is equal to 0 and then right is equal to
correct.
the length of sorted list.
So what's happening here? Yeah, you just said it. You just have to have the same number of commas on either side. So left equals 0, right equals this. Or you can say left equals 0 and then have a new line, right equals length. It's the same thing. It's just a different, shorter way of writing it. Typically, you'll see this if there's only 2 or 3. Once you get to 4 or 5, it's harder to read, and typically you won't do that. So this is 100% acceptable, though. I mean, it's pretty easy to read once you understand that, you're separating the variables and then you're separating those by commas. That's really all it is. So you can do it either way. So, and it doesn't hurt any computing time if you split your code up. And that's another kind of philosophy that I have with code. You're gonna, if you've been looking at Code Wars or any of these other sites that have these coding challenges, and then let's say you successfully do one, and then you see like the code other people wrote, and some of them are like elaborate, well, not really elaborate, but they're like one-liners doing, the same work that you took 15 lines of code to do, right? Well, that's great that it works and it's very efficient and it's awesome, but if no one on a development team can read it because it's too advanced for them, what good is it? And so sometimes having the code, written out a little more so it's human readable is kind of where you want to be. So another person, or so like a junior developer, if they can't read it, then they're never going to get their work done quickly. So you want to make sure that with, especially with like production code or on a team where you have all levels of developers, you want to make sure your code is readable. Now, if it's, maybe you and another person, you're both advanced coders and you're never going to open up your project to anybody else, fine. Use those, more concise statements that may be a little more hard to read. But in this case, this is fairly readable, but you could totally break this up into having two separate variable assignments. So either way, yeah. Is that cleared up there? Both 3 and 4? Cool. Okay, then we have linear time. Linear time is time or space consumption scales linearly with the input size. So as your input size gets bigger, your computing time grows, on par with it. So there's no like curve to the scale. So in this case, we have linear sum. We have in this case, we're defining this function, and we're bringing in an array or a list. And under the function, we're setting a new variable called total, and that's equal to 0. And then we're saying for num and array. So this is another kind of loop. We talked about these while loops up here, but now we'll have a for loop. And this one's like the most basic of the for loops that we talked about, the first one I introduced. And that's, for, and then we're making a temporary variable called num in array. So the incoming list. So we're saying for every item in array, we want to then go ahead and just add that total to num, or add num to the total. So we're saying total plus equals num. You could also write this as total equals total plus num. That's the same exact thing. This is just a shorter way, but it's universally accepted as the best way to write, incrementing stuff. In this case, we're incrementing by whatever num is. So every time the loop runs, num will change to each one. And then we return the total. So as long as this list grows in size, then this function is going to have to go over every single item. So as the list grows, it's just the complexity is going to grow with it. So if it's 10 million items, that means it's going to take, as long as it takes a CPU to go through 10 million calculations and, store everything in memory, it's going to take that time. So at the end, you get your sum result. So if I run this, then I get 15, right? That didn't take very long. If I were to grow this list up to, 1 million items, it may take a little longer. And I could show that here in a bit. So that one makes sense. Pretty easy. Awesome. This next one looks a little scary. I think I have this one right here. And so this one here is linearismic time. So what that means is it's time that grows. I can just show you a graph. Actually, it's probably easier that way. Let me see here. I think I have it at the bottom of this. Linearismic is O log n, right? Yeah. So it's pretty close to linear. So the first one was constant. So it's this flat line O of 1 right here, this red one. And then we had O log n, which grows very ever so slightly. Remember, I was talking about that list size, and you're splitting it in half and splitting it in half. You know, it's pretty close to constant. Or yeah, constant time. And then we have our linear time. So as the input size increases, then also our complexity increases. And now we're here at O n log n. So this one here is pretty close to linear, but it grows a little slightly faster. So it's still a fairly efficient algorithm. And you'll see this stuff is really tied to sorting algorithms. So let me go back to this. And I did want to take quite a bit to kind of explain what's happening here. And so if you look, this is a little more complex, and we're going to get to this level of complexity with our lottery example that we're going to continue. But we have two functions. So we have two. You can see this blue def here. We have two of them. And it looks like we have one called merge sort, and it's doing some stuff. And then you have merge, and it has left and right. So without doing nothing but just read the names of these functions, right? We go down here and we have a new variable on line 28 called sorted list, and it equals merge sort. And this is where basically this program is going to start. So it's going to, and you were to put all this into that Python tutor, you'll watch the arrows kind of go down to each definition, like of each function, and then go down to line 28. And then actually start. And then it's going to go back up to this function and actually put this array as the parameter in here. So this array, this is where everything starts after this call. So you're calling merge sort. And what it's doing, so let's take a look at what's happening here. So we're saying if the length of the array is less than or equal to 1, then we're returning the array. So we're going to stop everything right there and just return the array. So that's kind of like a catch-all, right? So we're saying, okay, well, if it's less than or equal to 1, it's already sorted. We don't need to sort anything. There's only one item in there, or there's no items in there. So it's kind of covering our bases. If that doesn't evaluate to true, we're going to go here and define mid. So we've seen that before. We defined mid, and we're going to say it's length of the array with the floor division of 2. Okay, cool. So we have floor division of 2. And we're defining left half and right half. So if we take a look here, there's something weird going on now. What do you see happening here? It's splitting it, but it's actually doing something different. If you take a look, what is this right here? So what is this green word, and then you have these parentheses? What is that? Yeah, Wes got it. The function is actually calling itself again. Yep, recursion. So Salvador put the word in there. It's called recursion. And so what's happening is, and this is something you don't, you're gonna see this, and just some of you are gonna be confused. You don't really have to worry about it, because you're gonna see it again and you're gonna understand it. Okay. But what's happening is this function is calling itself again. And what it's doing is it's then going in, it's going to be eventually breaking this down until it gets to this point. So it's going to keep splitting itself before it finally finishes. Just know that it can, Nika. I really wouldn't worry about it too much again, but this is how it gets the great time, because the way it calls itself. So we have it's defining these left and right halves, and it's splitting itself by calling itself again. And then if it still has a length greater than 1, it's going to split itself and call itself again. It's going to keep doing that until it drills all the way down. I have a pretty good visual for you to see how it's working, but just know that eventually it's going to return everything and then call this merge function. So it's calling left half and right half, and then it's going to merge everything. And so I kind of want to just show you how this works. And I think I have a pretty good example of it right here. Let's see if this is the one. Let me see if I can make this a tad bit bigger. What's that? Okay, can everybody see that? Or do I need to make it bigger? It's kind of like an echo. But if you take a look here, we have a list of actually 7 items, which is nice. And it splits the item in 2 halves. And then if you look, the left half is going to do all of its processing, because if you look at line 6, it says left half is merge sort. So it's going to call itself again, go down, do the split, hit left half again, go down, and do all that until it finally gets done. And then when it finally drills everything down, it's then you do right half and do the same thing. And so if you take a look here, it splits the first half once, and then it splits again until it can't be split any further. Basically, if the length of the array is equal to 1, return the array. Then it's going to then sort and merge them. So it's going to sort them, merge them, and then do the same thing there. Sort and merge, bring up, then merge these two in a way that they stay sorted, and then bring them back up, and then repeat the process with the second half. So this is kind of how it works. That if you notice here, this last one didn't have one, so it just stayed the same. So just returned back, and then sorted and merged, brought it up, and then sorted and merged the last piece. That's really what's happening here. I really wouldn't worry too much about what's going on. Just know that recursion is a thing, and you'll see it more and more. You can look up, you'll see some like developer cartoons over recursion, how you'll see like a process drilling down to smaller windows. But that's what makes this process so efficient. Yeah. Yes. That's the thing I thought when I first heard about recursion. But I really, again, I just want to show that the recursion process can help you efficiently sort something because the way it works. It branches down to the tree until it breaks it all the way down. I have another one that's pretty good. I just gotta see if I can find it. That shows it with like branches. Let's see if I have it up here. I don't know if I do. No, I have it somewhere. So again, with the merge sort function, you can perform merge sort on an input list, and it has a worst case time complexity of O n log n, which is pretty close to linear, which is good, especially with giant data sets. Recursion is your friend in those, but recursion can be a bit hard to wrap your mind around, especially in the beginning. Especially since you're just learning about data types right now. I didn't want to break it down too much, but yes, a function can call itself to drill down to a very root case, and then when that finally returns true, the whole stack will return true and build itself back up. So I'll find a pretty good one to visualize with Python Tutor. Maybe that will help. The next one is quadratic time, and that one is where the timer space consumption grows quadratically with the input size, or just with how many nested loops you have. So nesting your loops is where you start to go into the n, squared or n cubed time, and it just gets worse and worse. So let's go back to that diagram with all of those big O notation time complexities. If you notice now, we start to see this curve up, and it becomes more and more complex and takes more and more time. You have your O n squared, and then you can imagine that you have your O to n, your O n cubed, and then of course these kind of situations you don't want to run those type of operations on giant data sets, because it can overwhelm your resources. But for problems like you're seeing here with quick pass or with this entrance, feel free to use nested loops. You're not hurting your computer. It can handle it. We're with these, when you're thinking about this time complexity, with quadratic time or even longer, we're talking big data, lots of data points. So in this case, we have the bubble sort, and I have some illustrations of the different sorting algorithms, I think, right here. Yes, let me make this a little bigger. We can take a look at this. And so, we have the merge sort we've talked about. You have your bubble sort. There's other sorting algorithms as well. And what they do is, if you take a look at the merge sort, it splits them in half and then puts them together. See how long it doesn't take as long. But the bubble sort takes a little longer. Then you have your insertion, selection, sorting, and you can read about all these in online. I mean, these are, it's pretty good to think about these and how you would write programs. But you notice how the bubble sort kind of brings them up. Let me see if I can actually play a bigger one. There's one. It shows how it looks for the smaller ones and it increments up, and then it just moves them up through the data set. And the merge sort splits in half and then recursively comes back up and then finally finishes. So if you Google just sorting algorithm animation, there's like hundreds of sites to choose from. You can see them all. There's, some will go into detail over every single one. Some will kind of have everything played at once. So when you hit play all, you kind of see them all go and see how fast they finish based on how they're run and based on different types of data. So we have like few unique, and then we have a reversed, a nearly sorted, and then a random distribution. So it's kind of cool to see how fast they work based on the starting point of the data set, some of the other attributes of the data set. And so those, the quick sort, merge sort, bubble sort, all of those are examples of what you would see. And then, of course, you have your linear search and your binary search. So again, the binary kind of splits everything in half. So you have 1 and 2, and then it kind of keeps splitting down until you find your value. Linear search is kind of more traditionally the way you think of like computing, right? So when you're evaluating a list and you just want to look through a list one by one, you could do that and just kind of go through a whole loop of the list till you find your value or find whatever you need to do with your script that you've written. That would be linear. And so So yeah, that was pretty much a good introduction into some of the examples of big O notation. Does anybody have any questions over what we've gone over so far? And what's nice is if you want to take further time to kind of figure out how this is working, you have this. You can always go back to this uh, this this repo. We're going to have it open. There will be some changes with it, probably some different examples as we further as we further develop this. And again, don't read too much into it right now because I'm not expecting you to understand everything here that's going on right now. We're just trying to measure on those 4 things that we talked about, right? But this kind of shows, how you can use a programming language to kind of do some pretty creative stuff, right? Who the heck figured out that you could, call a function inside of a function and then that actually gives you a more efficient search? Like, I would have known. I'm glad someone else figured it out for me, so I don't have to. So, so yeah, it's pretty cool how these work. So, but y'all seen this before. Y'all seen the nested loops. And again, I think you heard me mention it. I was like, yeah, nesting loop is a good like first stab at something, right? But if you can find something else, like maybe a binary search or recursive function, that's even better. But if somebody's trying to give you a challenge or something to do, and you're trying to just quickly see if you can get it done, if you reach for your nested loops, initially, and it works, great. You have something that works at least. And that's kind of what we're going to be doing with the Powerball simulator, right? We're going to try and get it together, the MVP, if you will, the minimum viable product. We're going to get it working, and then we can fine tune it and maybe change our code a little bit, do some refining to see if we can get it to run a little more efficiently, make it look prettier. So have it like maybe prompt the user for some stuff if they want to pick numbers for their ticket, so on and so forth. So, and I mentioned some of the stuff about like, time efficiency. There are Python libraries for profiling code for complexity, whether it be time complexity or memory complexity. So this memory profiler, this one's pretty cool. I actually went into my test module and took a look at it. So here I have, I imported memory profile, and I just put the bubble sort in here just to see, what it would do. And let me see if I remember. I think it's this one here. So here it kind of shows and if you can't read it, let me make it a little bigger here. There we go. Here it kind of shows you the memory usage per line. Of what it's using for memory, and I have even another one. Let me see if I can put this other one back in. Let me see. Is it bubble sort? I think it's bubble sort. Yeah, let's do this one here. Oh, that is bubble sort. Never mind. Let's do. Remember which one I had for this one. Give me 1 second. We can take a look at this one. Let's see what this one does. I don't think I need that. I just need this. Let's see what happens when I run that. See. Oh, it's that one. That one's also profiles the same way. So it uses, Only really in line 3, it kind of saves it only uses 42.7 for the actual function. Then the rest of the time it doesn't add anymore. So I'll have to find one that goes there. I had another one there. I just can't remember which one it is right now. But that one is your memory profile. I showed you C profile last class, which kind of gave us what did it give us? I'm trying to remember. Gosh, I'm drawing a blank. I showed that to you last time. I'll have to pull it up again. It's in the video. And then time it, which gives you your execution time. So you can kind of evaluate. You can actually see the efficiency of these by running time it on them, and it gives you time in like milliseconds. So it's really fast. And you can see which ones are operate much faster than others, depending on what state you have. So, and so, again, this is just a quick overview of some of these concepts. And this isn't, we're not meant to go into depth over everything, but hopefully it kind of gave you, some look into, at least a peek into how you can use that, the different attributes of how Python runs, and how the stack operates to maybe make your algorithms run a little faster. And not now, but this will be, you get into Whiskey Platoon, and you're in there, you're going to see this stuff again, and they're going to go into a lot more depth with you, and show you some cool tips and tricks and how to use it. So any questions on what we've gone over in this lesson? Okay, let's go ahead and it's almost 7 now, so let's go ahead and take a 10-minute break and come back at 7:05. Oh, there we go. Rigo gave us looks like a PDF. I'm going to take a look at that. Oh yeah, look at that. I have no idea if this is totally just grabbing it or if the author allows it, but yeah, you have that. So yeah, let's go ahead and take a break. Gotta come back at 7:05, and then we can resume going over the lottery simulator. I'm gonna pause the recording. All right, welcome back from the break. Again, before the break, we went over big O notation, some concepts with it. I think kind of showed some pretty cool things you can do with Python to kind of help improve your computation time. Using either like recursion or some other tricks to kind of like split lists if you were trying to search for something and split them in half versus just going through them one by one, which is what we normally think a computer always does. It doesn't have to. So it's a good introduction to some of those concepts that will be further built upon in the cohort when you attend Whiskey Platoon. For the rest of the class, for the next 2 hours, we're going to keep exploring this lottery generator. So if you remember from week 8, we decided we're going to build something that simulates how the Powerball works. And if you don't play the lottery, this kind of gives you some insight in how it works. But basically, we have five random, 5 balls are pulled out of this hopper. You know, if you ever seen like a snippet from a lottery, it has this big bin and air's blowing in there and the balls are going everywhere, and then you know it just pulls one out, and then that's the lottery. They pulled 5 of those, and they have a special hopper that has, you know, the Powerballs, and then the Powerball comes out, and that's your final result. If you've looked into lottery, played it, you know that, you know, they say it's about a 1 in 300 million, you know, chance of getting all 5 numbers plus the Powerball, and that is true, considering how sometimes it grows to over $1 billion, and then someone, you know, basically wins life-changing money, but your chances of winning it are extremely slim. But we're going to simulate that with this. And so last session we kind of went through the thought exercise of how do we, you know, conjure a ticket, you know, with Python. How do we pull this out of thin air and make a ticket? And you know, we had to go through and think about, you know, we take this problem, break it down to several sub problems, like, okay, well, you know, what kind of data type are we looking at? You know, what's going to be the best type for that? And we decided that we wanted tuples for our ticket because they're unchanged. Once you define them as something, it stays, and that's perfectly acceptable. You could also have them as a list. I don't think in our script really changing them anyway, but you know, in that we actually build it with a list, then convert it to a tuple at the end. So just to revisit kind of what we came up with, because all we want to do is build a ticket. And at the very end, I was like, wait a minute, you know, we know that, you know, we're generating a ticket, but can we use this logic to also generate a drawing? Because it looks like it would work. And we're like, yes. And so, you know, we imported, you know, going line by line, we imported random, which is a module that gives us pseudo random numbers. And we use mainly just one method in there, and that's the randint method. And then we can give it the constraints of, you know, the initial hopper for the main 5 balls that come out. And then we have a separate hopper for the Powerball, which is 1 through 26. But we started thinking, okay, well, how do we build a list of 5 numbers? Like, well, we can just have it run 5 times. And we initially built a loop. And then, you know, as we're thinking about the problem, all of a sudden, wait, does the Powerball have repeat numbers? Well, no, it can't have repeat numbers because it's a hopper of those 75 balls. Once one of them's removed, you can't ever get it again because it's been removed. So we had to kind of go back to the problem and say, well, actually, we can't do that. We have to actually, you know, check this thing as it's being built, make sure it's not repeating numbers. Of course, I also highlight the fact that what we're doing of this doesn't quite mathematically match how the Powerball works, but right now it's a good first solution. So, you know, we're still getting random numbers between 1 and 75. However, if we're doing a repeat drawing because we hit the same one, then obviously we're not having the same mathematical odds, but we're approximating right now. We're going to get kind of close. So we're doing that, and we're actually building tickets. And so at the end, you know, we get the 5 numbers. They're all going to be different from each other. So you get 5 unique numbers from the collection of 75 numbers. And then after that while loop runs and finally we get to our length of 5, we need to return the Powerball. So the Powerball is just calling this, we're just calling the random.randint method again, but only going 1 to 26 and just appending that to the list and then converting it to a tuple. And that is our ticket. And so we actually can then just say, well, my ticket is ticket generation, and we don't have any parameters in it because we just want to run the function. And then we're like, oh, wait, we can actually just make the drawing. And so we have the drawing, and it's, you know, ticket gen. And now we have both. And I showed that when I ran this cell, we actually get 2 unique tickets. You know, one is a drawing, one's a ticket, and we just compare them, right? And so that's I started writing day 2 goals earlier today, but you know, I was working as well, so I had to, you know, I didn't really get through it. But we have to think, okay, so what can we get done in day 2? We've already now gotten tickets, got drawings, but we have a lot to do. We still have to, you know, we have to compare them. We have to think of, how we're going to, if we go back to our MVP, it says we should generate a user's ticket based on a pseudo random number generator. And we need to ask the user how many times they want to play. So we need to do that and execute that number of drawings. Okay. And tally how many times the player hit a winning drawing. So we have to think about the prizes. How are we going to calculate winning prizes? How do we get through that logic? And it should also print out when the user hits the jackpot. And then we can even maybe return a summary of the winnings based on the number of drawings. And so we have to think about these data types and how we're going to do that. So, but right now we have a way to get a ticket. So that's kind of cool. Any questions on our progress so far with that? Okay, cool. So let's think about making this a little cleaner, right? So we have our tickets and we say it's ticket generation, but really it's not a ticket generator. It's kind of like the number generator, or we can call it anything. We can keep it a ticket generator, it's fine, but we're actually using to generate drawings as well. Let's just call it random gen. So let's just call it random gen, because we want to kind of make sure it's kind of separate. It's not just generating tickets, it's generating both. So it's a random gen. And we'll name that random gen. And so let's go ahead and maybe work on making this a little more user-friendly. So with that, we can maybe start using the console to kind of get tickets, or maybe hit this part of the MVP where we start looking at user input to get like how many times you want to play or something like that. So let's go there. And I don't think we'll need to write a function more, at least right now, but at least we can just kind of have, we can write some code in here. We can write some code in here to, prompt the user for some stuff, right? So Athena asked, do you want the drawing to stay the same each time you play? Well, we could have maybe the ticket stay the same, right? So let's say, because you can buy a Powerball and say you want it valid for X number of drawings, right? So you have, because let's say you have a certain set of numbers that or mean something to you. Some people do that. They'll actually fill out the little form. It doesn't give them any better odds than someone getting a quick pick, but they can do that. Some people do like birthdays, but if you think about it, like you almost like your chances are higher of like selecting birthdays, because other people also select birthdays. So I would assume that more people would select numbers below 31 or 31 and below than the higher numbers, because they're using names. So you have a higher chance of using those numbers of splitting a jackpot with somebody than having your own jackpot. That's kind of something to think about. But anyway, oh, so you're confused. Yeah, so like the ticket, ticket will stay the same, but we can call random gen on like any number of drawings. We can keep the ticket the same. So let's start there. Let's think about how we can maybe prompt a user. Has anybody, I know we've shown it. Does anybody remember how you would like get something from a user with like a Python script? Yeah, input. Input is exactly what you would do. Yep. So you can say, well, you can just define like we can define a variable. So let's start with like, we're not going to have the user pick numbers or anything. We can do that, but right now we're just going to worry about getting like the number of drawings that we want. So we could say, okay, well, num drawings And we can say that's equal to input. And then we can say how many drawings would you like? Maybe enter. Let's give it a limit. So let's say enter number between 1 and 10. Okay, and right now I just want to see if it works. So print num drawings. Try that. Okay, this is kind of weird. Jupyter Notebooks kind of pops up there at the top. How many drawings would you like to enter? Number between 1 and 10. Well, let's just do 6. Enter. And then it comes back out and prints number of drawings. So it looks like we have it. We have 6. We've saved now num drawings is part of an input. So we have that. So then all we would need to do, let's see, all we would need to do now is then get a ticket. So we can say, after that's run, we have our num drawings. So we can say the ticket equals random gen. And then we have a ticket. And now we need to get the drawings. We want to do the number of drawings. How can we then get a collection of drawings based on the number of drawings the user gave? How would I do that? Dictionary? How would I add that to dictionary? We do the drawing number and assign it to the ticket that's created. Okay. What if we just built a collection of tickets or drawings and we can just save them to compare them later for now? Like I have another way we're gonna do this, but for now we can just collect the drawings and put them into a collection, whether it be a dictionary, whether it be a list. Maybe we can do a list of drawings, so a list of lists that have all the numbers kind of collected. So we can try and do that first, maybe. So maybe we can say drawings equals for number of drawing in range, num drawings, append num of drawings. So for let's define, I guess, total drawings equals empty list, and then we do our for loop here. Okay, so it would be for drawing in num drawings, like that. Total we can say, okay, so it makes sense. Let's try it. So for drawing and them drawings, append or total drawings, append drawing. Oh yeah, you didn't use ticket gen. Okay, so we can say, so for drawing, and so we can say, well, see, num drawings, what is that? What type of data is num drawings? Int? Int? We say it's integer? Let's check. Let's check before we move on to make sure we know what it is. So let's do type num drawings. So if we print that, so if we run this, it's going to give me the prompt, and I can say 6 again, hit enter. And then it says it's a string. So we have a string. Well, snap. Exactly. What do we do? I mean, I have a string. I don't want a string. I want an integer. I want the number. Oh, perfect. So Nika says we can cast it. We can just change it, right? We have that ability. We have the power. So we can say num drawings equals int num drawings. So now we have an integer. And then we have our ticket. That's good. We can do total drawings. And then now we can say for drawing and num drawings, because no num drawings an integer. Is that going to work? Is this the right kind of for loop for that? We could try it. So we need to use ticket gen. Okay, so how about so total drawings dot append ticket gen. Let me see if that's right. Oh, random gen. Sorry, I already used the old name. Random gen, right? Random gen. Because it should return a tuple, so I can append a tuple to total drawings. And then we just want to go through that and then print, just see if we get our drawings. Like that. So we're going through, we're making an empty list to kind of put stuff into, right? And then we say, well, we want to make a loop. So we for drawing and num drawings, total drawings, append, random gen. And then we can print. So who thinks this is going to work? Like, got it first time, right out the gate. We're good to go. Let me clear these outputs. I can't. Okay. If I hit play, let's see. Okay, we want to say 6 drawings. Enter. Ooh, we got an error. We got a type error. Okay, so it looks like here it's our for loop. Darn it! So line 20, our for loop is saying int object is not iterable. That's right. We can't iterate over an integer. Ah, Athena's got it. We got to put range because the range function creates an iterable based on your input. And in our input, we can do up to 3 things, right? We can do the start, the stop, well, the start and the step, but the stop, the stop is the only required one, and that is going to be, if you have only one in there, it's going to be your stop, and it's going to default the start to 0 and the step to 1. So it's going to be in the range. So in this case, we are going to go up to, but not include the last number. So we're going to get the drawing. So for drawing in range, num drawings. In fact, if we're using range, we just want to say for I or index. So you'll see it sometimes IDX or I, either way, because we're really going to be making indexes. So for I and range num drawings, and we just want to use that to iterate, and then we're just going to append. So I think this will work. We run this. Oh, need to go ahead and do my input. And look at there. We have a list of tuples, and it looks like we have our drawings in there. We now we have them saved in a variable, and we can reference them later if we want to. So there we go. We have some basic functionality now. We have a user, to put number in. Please enter a number between 1 and 10. It's very brittle though. This is very, very brittle because there's nothing saying the user has to put in a number. Let me see here. So if I were to run this again, for example, and say, well, I want 6, then it's going to give me an error and tell me that it doesn't know how to do anything like cast the number 6. So yeah, when you do maybe some data, yeah, we can make sure you can only put in 1 to 10. We can sanitize the input. Yeah, we can maybe have some lookup tables for some potential entries. Maybe I would say probably not. We probably need another way. But right now we're fine because we're just right now trying to get something to work, even though it's kind of brittle. But we can maybe worry about that when we fine tune it, right? Yeah, we can. There is a way to make sure they can only put in 1 through 10. One of the ways we can put this prompt in a while loop, and then we can say, while the variable is, while it's not equal to a or we can put a Boolean statement in there just as, until their variable is, if it's not equal to a integer in the range of 1 to 10, it's going to keep just asking and just give them like, hey, that doesn't work, try again, please enter a number between 1 and 10. Eventually when they do, it moves through the rest of the logic. So you can kind of trap them in a while loop. That's one way you can do it. But in this case, we have a brittle solution, but we have a solution, and that's all that matters right now. So right now we can ask the user how many tickets they want, or drawings they want. They have a ticket that stays the same, and we have a collection of drawings that we can then, yeah, that'll teach them the rest of this. We have a way to, get drawings, compare them to the ticket, at least somehow. I don't know how we're going to compare them yet, but we have our data. Now we can then move into maybe making like another function, if we will, right, to compare. So but let's go ahead and like maybe just try with one, because right now we just really want to compare a ticket to a drawing and see if we have any matches. That's a pretty simple statement to make. Like, oh, I just want to compare my ticket to my drawing and see if I have any matches. Like, it's cool. But how do we even implement that? Where do we start? Where do we begin? Any suggestions? If not, it's okay. We can. Yep, we want to compare the ticket to those lottery numbers. Okay, so Athena says if in statements. Yeah, maybe we can do that. Maybe we'll involve like a loop, maybe looping over some stuff. There's some attributes about this. It's kind of cool about our data. Right now, we know in our tuples, the last number is the Powerball. It's always the Powerball because the way it's built. And remember, tuples are collections that maintain their order. So that's good for us because then we can just kind of maybe work on the first five and do some comparisons there. The first five, we don't know what order they're going to be in, right? So while 48 may be the first one on our ticket, the 48 we're looking for in a drawing, which may match, may be the fourth one. And so we need to somehow figure that out. And I think doing like if we loop over one of them and see if the value is in the other one, then we can maybe just count how many matches we have. We can compare them, but remember, they're not ordered. So two tuples may have the same values but in different order. And if you check for equality, they're not going to be equal. So you have to compare the items in the tuple. And that's why we're going to probably have to do some sort of loop. But it's not a bad thing. It's not, I wouldn't say it's an ouch. It's pretty easy. We're just gonna build a loop, right? So let's make a, and if we're going to be doing this process, so we're right now we want to get anywhere from 1 to 10 tickets. So this is a repeatable process. I would say we should probably make another function that we can call to do a compare. And so I kind of already made some room on line 16 here to make another function. And so remember, we write functions just like we have on line 3. We want to use the def keyword. And we're going to call this compare. We can just call it def compare, right? Do we have any inputs to this function? Do we need to put anything into the function to get a certain output? The ticket? Okay, so cool. Ticket and the drawing. Okay, so ticket and drawing. Right now with our drawings, with what our user is inputting, we could get several drawings. So we're actually, what's the data type going to be that total drawings is going to be? What is the data type of total drawings after we get our drawings? Jacob asking, okay, so are you talking about these items in orange that I'm putting in right here? Is that what you're asking about? So those are not notes for the reader. These are, do you remember what these are called inside of these parentheses when you have a function? What's the official term for that? Parameters, right? So these are parameters that go into a function. These are going to be something you define, and whatever's going into the function gets named this thing. So with our first function, we had no parameters, so we didn't have to worry about it, right? But in this case, now we want to do something with some inputs. So these are inputs into the function. We have our ticket and our drawing. When the function runs, anything that goes in there, ticket's not always going to be the same, and drawing is not always going to be the same. But it doesn't matter because when the function runs, that's what they'll be called inside the function. Only inside the function, not outside the function. So it's going to have a scope of inside the function. So in this case, now, and I can show you. So let's just print the ticket. And then print the drawing. So we can start there. Yeah, so the function will keep track of them. But, just remember when you're inside of a function, what you're doing is you're building kind of like an isolated little, applet, if you will, or a tiny little program that runs on its own, and it has its own little world inside this function. The rest of this logic doesn't care what's inside this function. Only the function cares about what's inside of the function. The only thing that when we call, what we want is a result of that function. So when like, for example, whenever I want a ticket, right? I really don't care what's going on in here. All I care about is that the ticket is going to equal a tuple that is 6 items long. The first 5 will be randomly selected numbers between 1 and 75, and the last number will be a random number between 1 and 26. All I know is I know what's coming out of the function. This logic here has no idea what's happening inside of random gen. It just knows it can call it and they can get stuff. Just like when you go to the bank and you know what's going to happen when you go to the bank and you give them money. You give them something. You say, hey, bank, do your thing with the deposit. So call the deposit function. And my parameter is my money. And so you're saying, hey, bank, deposit this $500, right? You expect the output to be your bank account balance going up by $500. So the output of that is your bank account. You don't care how they do it. You don't care if they say, oh, cool, thanks for the $500. Now let us go ahead and deposit these $501 bills into the safe where your account is, which is silly. It's not how it works now, but you don't care how they do it. You just want to get that piece of paper saying, okay, $500 has been added to your account. So yeah, it's a black box to everything else. So that's how the functions work. So we're inside here, we just know that in compare, we have a ticket and we have a drawing. And now we're gonna define what's happening in a black box. The rest of the logic doesn't care. And so in this case, right now, we just want to see it printed out. And so with that, we have our total drawings. So we can go ahead and get rid of that. And now we can say compare. This is where, again, we are just giving it the inputs we expect an output. So compare, and we have the ticket because we're giving it the ticket and we're giving it total drawings. Okay. So again, we're calling the function and we're going to give it the ticket that came out of this random generator, and then we're going to give it total drawings, which was the whole bunch of them. And so now if we run this, I'm going to get my input and I'm going to say, I'm just going to do 2 this time. Enter. Boom, boom. Got it. And look at that. So inside of compare, when compare ran, it printed the ticket and then it printed the drawing. Okay. It's probably better to say drawings because we may have more than one. Perfect. Yeah, this is exactly like functions is part of it. So making sure this clicks is really good. And so that's why I wanted to have something that has multiple functions so we can see how that it's like a black box, everything else, but we put those parameters in. It was named the ticket here, but inside the function calls it ticket. It doesn't matter what it's called here. It can be called anything, but it just needs to have the right data type, if you will. So you are assuming that we have to put the ticket here? Or could we just do this? You're saying that, right? As ticket. You could. 100% you could do that. But the problem with that is if you're not saving it in memory somewhere, how are you going to access it again for other things? So in this case, we have all of our drawings. I mean, sometimes that is, but I mean, I've always defined my variables in case I need them for anything, but you could do this. I mean, I think this will run. So if I ran this and I gave it a 2, hit enter, it runs. It runs just fine. Let me just make sure it runs by saving it. Do that again. 2, enter. Yeah, it runs. So it runs by doing that, but again, we want to save this ticket for other things. So we have other things we're going to be using for it. So I think the safer bet is defined as a variable, so we can reference it outside of that function. That's reminding me about saving it so we can use it in other places. Maybe me thinking about it, taking up the same ID in memory. I mean, it will always be in the same location in memory once it's instantiated as a variable. Ticket. Let's put it back to the ticket for now. So in our function right now, all we're doing is printing. We don't want to do just that. We want to do some comparing. So we need to add like more logic in here. So what can we do? So maybe we can do what do y'all think? How can we compare the ticket to the drawings? And right now, let's assume we can have either 1 or 2 drawings. That way we know we have the right data structure. What is the data structure of drawings again? Can sort it or cast it to a set. I don't think you can't cast a ticket to a set. Do you know why? So Athena, again, the tickets could be out of order, but still match. So again, numbers matching is a thing. But you can't cast a ticket to a set because you may have a repeating number because the Powerball may match one of the numbers. And if you cast to a set, you lose one of those, but you don't know which one you lose. So you can't cast it to a set. But we know they're both going to be the same length. And we also know that the Powerball is always going to be at the end. Yep, yeah. So sets, remember, you're only unique numbers, but you may have the same number in a Powerball ticket if you keep it in the same data type. So we could possibly just loop over one of them, either the drawing or the ticket, and do some comparison. So we have our let's say we loop over our ticket because we know we can loop over the ticket, but we may need to, because we can have more than one drawing to loop over. Maybe we could loop over the drawings initially and then do our comparison, because remember the drawings is going to be a list of tuples. So it's going to be, a list of, up to 10 objects, or not objects, but items. And each item is a tuple or a drawing that we need to loop over. So maybe we can do a loop. Well, again, if you're comparing a ticket to a drawing, we have to actually go inside of each ticket. Are you talking about ticket at the index of 0 equals drawing at the index of 0? So the problem is if you take a look here, if you look at this drawing right here, right? You see how they're not in order? So you have a 6 here. And then, like, what if you match your ticket, but your 6 is here? Then those indexes won't match. But we could do membership and then count matches. We don't care like that, and we can't sort tuples. Nope. Actually, I think you can't sort them because you can't change them in place. But I'll check that because you may be able to sort them without actually defining it and just kind of see it. But I can't remember off the top of my head. Again, that's why I always look back at it. But I don't think we have to sort them. I don't even think we have to do that. I think we could just loop over the ticket. First loop over the drawings, right? So for drawing and drawings, so we're looping over each one. We're getting the first tuple, and then now we can loop over for number in ticket. If num in drawing what do you want to do? So if you're not following what I'm doing here, I'm first looping over the drawings. I may have more than one. And so I'm isolating one of them, the first one. So I'm getting the first drawing. And then when I have that first drawing, I'm going to go look at each number in ticket. And I'm going to see if that number is in my drawing. And I'm checking for membership. And so if the number is in the drawing, we can maybe start by just printing a celebration. So let's do print match. We can try that first, just to see if we get something. And I don't think this is perfect, but I think it at least gets a starting point. We're actually checking to see. We're going to be comparing tickets to the drawing. But we have to consider the fact that we're comparing Powerball to Powerball only, not Powerball to something else. So we have to think about that. But right now, we're just trying to see if we can see any matches. And let's go ahead and play this. And then let's just do 10 drawings so we can kind of make sure we at least see match prints once or twice. So enter. Oh, we got 4 matches. So 4 matches and 10 drawings. We don't know if these 4 were in one drawing, but we saw a match. Something happened. So we have 4 times we hit a number that matched from a ticket to a drawing, but we don't know right now. We know nothing, but we know at least that logic works somehow, and in some way. Can we make this print statement, or maybe add another print statement that makes it to where we can see stuff? Maybe. Just to see if we're on the right track. Yeah, we could do an F string, or we can just, if we hit a match, we can just print ticket and drawing to see what matches. Yeah, so print the ticket. So we can just say print ticket. And then we can also print drawing. Drawing. Yeah, drawing. That's right. Yep. Let's play it again. Do 10 again. Okay. So it looks like we have some matches here. A whole bunch of matches. Wow. Okay. So in this case, we had a match with this. This is our ticket. It doesn't change. See how it doesn't change at all? And then it looks like in this drawing, we had a match here. So 71 matched. And then it looks like So it goes over the ticket, 22, 60. So 60 matched, and then 71 matched. And you see how, so it matched two numbers, and that's it. Two numbers in this 5, and it doesn't matter the order. See how they're in different order? Because I'm just looking at this and seeing if it's in here. And then I'm looking at this and seeing if it's in here. Oh, it is. I have a match. And then I look at this, see if it's in here. And then I look at this and I see if it's in here. And oh, there it is, 71. I found a match. Looks like I'll be putting 60 on my next ticket. Yeah, because it looks like it matches down here too, right? And it matches here. Yeah, so it's crazy. We got some lots of matches. And 60 looks like there's our crazy one. Okay. So cool. So we know that now it looks like it's matching them, and it's matching them if it's not in the same order. But we didn't account for the Powerball yet. So how could we tackle that? I don't want to match the Powerball to the first 5 numbers. So I never want this this number to match any of these, even if there is a 2. I only want to compare the last one to the last one. If you notice, that's actually what our match was the first time, was the Powerball. It happened to just match perfectly, even though we didn't have the logic that way. It just, by luck, we hit the Powerball. But remove it to assign, we can do that. Yeah, we could totally do that. We could remove it. Now we can't pop it because you can't change. So the goal of Powerball, of course, to get the jackpot, is to match everything. The entire ticket has to match the Powerball drawing. I will guarantee it never happens in our testing, no matter how many times we test. We will never see it match while we're developing it. Now, when we finally get everything run and we do millions of drawings at once, we may see a jackpot. I mean, I've seen it when I've done this before. I think this is what we're gonna build. We're gonna build this, the whole thing. You have to hope, yeah. If we hit it, like, we're not gonna win anything, but it's it's not the official one. But you're gonna see how incredibly unlikely it is. Like, you win some homework. Before I move on, since we kind of stopped here, does anybody need to take a break? Because we've been going at this about 50 minutes, but we can take a small break if we need to. Otherwise, I can press. I'm recording this, so we don't have to.
Hey, Aaron, could you just explain quickly again that function right there with the ticket and the drawings? It's self-contained, but could you just explain those again?
Yeah. And so what I'm doing by writing this is I'm saying, hey, I want to build some separated logic from everything else that does something. It takes an input and then it does a bunch of stuff, and then it gives an output. And so when I say ticket and drawings, like, in this function, that's what these will be assigned. But what I actually feed the function could be named something else outside of the function. It's going to get renamed inside the function, its own little world. So when I give it the ticket, right, that's because the ticket is the result of this other function, this random generator. So we ran this generator, we got a ticket, we have it saved in memory. I'm feeding that same ticket into this compare function, but it gets renamed inside the function, only inside the function, not really. Outside, it's still called the ticket, but inside the function, it's then being used in this logic we're building now.
Got it. Okay. That makes much more sense. Thank you.
Yeah, and so we're creating isolated logic to then like give a result. And as we build this, the whole point of doing this is to get like a result out that we can add to something that collects results to then tally up and give us like, money won, or how many times we won the Powerball, or how many times we won 3 numbers out of 5. We can build that in here. And so right now we're just trying to build to result. And what I'm doing right now is I'm slowly building this logic to show that, okay, we can do this basic functionality. We've broken this problem. Like, we want to compare tickets. How do we do that? Well, we need to go down to the very basic number of each ticket, right? And each number, we need to look at that number and see if it's in this other one. And if it is, we want to do something. If it's not, then don't do something, or do something else. And so you'll see that what we can do then is we can then get a result out of this, which is like maybe number of matches, and then we can put that into a dictionary that contains like matches and prizes, and then start incrementing like the money won with how much money we won, per drawing, and we can then add that to a total. So so Nika, you're talking about if we loop, like maybe we can just loop it looks like up to, so a slice up to but not including the last one. That's for num and ticket. So you want to take a slice out of it. So instead of for num and ticket, we want to say for num and ticket like that. I think you're on the right track, but you also need to do the same thing for drawing. So, because you don't want to compare the last number in drawing, so you want to do that as well. And Athena says you can cast it to a list and then pop it and then change it back to, you can do that too. I would say this one is probably cleaner for this because we don't have to do anything to it. All we're doing is taking a slice of it, which we can do with tuples. And then we can check to see if we've matched. After that, then we can say at the end, so for num and ticket, we finish that. We could then say if ticket -1 equals drawing -1, print so we can loop over up to but not including the so just through the first 5 numbers. And then after that's done, then we can just check the last number in a standalone if statement. And then we can print Powerball match. And then we can say print ticket drawing. Oh, this is a cool one because it hit both. Look at that. So here we have 59. So we first checked the first 5. and the 59 matched, it hit. And then once it got done, it checked the Powerball, and the Powerball matched. And then we had 2 matches. So that worked. So now we know we have matches. So this one would have won. I can't remember what the prizes are. I have to look it up again. I've built this so many times. I think it's like $4. I can't remember. I could pull up the Powerball result winnings actually. Let me do that real quick. Window. Powerball prize table. Price chart. Here's the Powerball price chart. So we need to convert this into code eventually. So we're not going to, also there's power play, which we're not going to do. We're only going to say no power play. So here's the example. Yeah. So if you get the Powerball only, you get $4. If you get one number plus Powerball, it's $4. 2 numbers is $7. Just 3 numbers without Powerball is $7. 3 numbers plus the Powerball is $100. 4 numbers by themselves without the Powerball is also $100. And then 4 numbers plus Powerball, 50,000. Only 5 numbers, no Powerball is $1 million. And then matching everything is the grand prize. And then here's the corresponding odds. So 292 million roughly. I don't know if y'all can see that or not. Let me make it bigger. It is very unfair. And here's the overall odds are 1 in 24. So a prize. So most likely, of course, these $4 prizes. It's slightly better than playing roulette on a single number. So just like putting your guess on a single number. I think a single number for roulette's like 1 in 36, I think. But in Nevada, you have all sorts of other gambling you can do if you want to gamble. Me, I'm actually a poker player, so I like to play other people. I don't really care to play against the house because you can actually have a bit of skill involved with poker because you're playing other people. The casino makes their money by taking rakes out of pots. So they just take a portion of the pot every time it goes over a certain amount. So that's how they make their money in poker. It's definitely not as much as slots or roulette or blackjack, but so let's go back to here. We have our compare. Looks like we can get matches, but we need to go a little further because we want to, start like collecting information to then get to some prizes. Let's go back and just remind ourselves what we're doing. So it should generate static user ticket based on a pseudo-random number generator. Ask the user how many times they want to play, and based on information, execute the desired number of drawings. Okay, we can do that right now. The program should tally how many times a player hit a winning drawing. So we're kind of doing that. We're matching, but we don't necessarily have a winning drawing yet, because if we just hit a single number, that's not a winning drawing. You don't win anything for that. So we have to kind of consider how we're going to determine a winning drawing versus just a number that matches. So we need to add more logic in here. So based on that table, again, if you hit just a single number, it doesn't mean anything. But we already have the Powerball split. So we know when we have the Powerball, and we know when we're hitting a normal number, and we can see that. We just need to collect that data. And so how can we collect that data with this compare function? Well, see, we're already doing ticket equals, we're kind of doing that with this logic. So we're seeing if the ticket does equal the drawing, but we're doing it in a way where we can compare each number because they may be out of order. But now we need to actually, because we have our price chart here, we need to maybe see how many we're matching in a single drawing and maybe collect that information to then determine if we have a winning ticket. All we need to know is if we have a winning ticket. We don't need to know how much. We just need to know if it's a winning ticket. Okay, so Athena says a match counter and a Powerball counter. Okay. That sounds like something maybe we could do. So maybe make some new variables up here. So like match counter equals 0. And then Powerball. Well, I don't think we need a counter. We just need maybe like a Boolean. Right? So if we hit the Powerball, we know it's true. And we can just change it to true. And we know we've hit the Powerball at that point. You could also do it 0, 1, doesn't really matter. But in this case, we're just introducing another data type that we can use and kind of think about how we can use it. And so we have our match counter and we have Powerball. And so now we can just inject this logic or these variables into here, change them depending on what we have. So for number in ticket, if number in drawing, now we can still print match, but we could also just get rid of that because we know it works now. So we can say match counter plus equals 1. And then here, Powerball equals true. And then we can maybe just print both of them. If you notice here, I'm going back to this line right here because I want to finish going over the ticket and I want to finish the logic with the Powerball. I don't know why it's not accessed. So we have Powerball equals false. And we're reassigning it. It's the same name. Literal false. So here we can print match counter. There we go. We can then print Powerball. And I'm just gonna do 100 drawings, that way we can see it. Okay, so truncated because there's a lot of matches, but looks like here I had 3 matches. It looks like I'm building something, I'm doing something wrong. Looks like it's incrementing up. You see that? So I'm doing it and I'm counting it up. How could I have 28? Like, it looks like I'm printing out 28 at the end. And then it looks like it's false, 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 true. And then it stays true. Maybe I can just print, maybe I can print match counter here and see what's happening. I shouldn't get a 28, right? Oh, match counter needs to max out at 5, okay? Right, I don't want it to keep going. In fact, I mean, if it maxes out, I mean, that's a really good prize already, but let's do 100 again just to kind of see. 1, 2, 31, 30. So it keeps going up. Yeah. So I need to max out, so I need to somehow reset it. Because I'm incrementing here. So if it matches, I'm incrementing it. I don't think I want to put it back to 0 once it hits 5, because most likely I'm never going to hit 5. I mean, I could in the same drawing, but I think I want to reset it probably every time it goes over to a new drawing. Because remember, I have a collection of drawings, right? And I'm iterating over that big collection. And when I iterate over each one, then I'm checking the numbers, right? So when I get done checking the numbers and checking the Powerball, when I go back to this iteration here, I actually want to make match counter equals 0 there. And then it'll reset and then start checking a ticket. I think the print is fine because that's when it gets done with a drawing. So it finishes comparing the numbers, and then at the end of that, it gives me the print. So let me run this and just do 10 times again. There we go. So it's a matching 1, no Powerball, and then going back to 0. Matching 1, checking Powerball, no, back to 0. So then it's doing it right. Oh yeah, so if I match the Powerball, I want to print it, but then immediately I want to make it false here too. So that tells me I probably don't even need it up here because I'm checking it per drawing. I don't really need. Okay, we can slow down. Just fine. We can, we're taking this, in small bites, right? So if you remember when we're going over this and doing a comparison, we're pulling in all of the drawings. So however many drawings a user wants, we want to put into this function. And remember, this data type is a list of tuples. So if you think about it, when I make this loop, what I'm doing is I'm saying, okay, now I have a collection of drawings. I want my first drawing. So the first drawing happens. It means I have a tuple, and it's going to be the drawing, one of the drawings. And then I'm comparing that to a ticket. So this logic here is where that magic happens right here. So first, I'm just getting one drawing and then one ticket. And I'm saying, okay, cool. I want to go ahead and make match counter equal to 0 and Powerball equals false because I haven't done any comparing yet. I just have a starting point. And then I'm going into a nested for loop, and I'm saying for number in ticket up to, but not including the last one. So the first 5 numbers of that ticket, I want to start doing my comparing. So here I want to compare. And so for each number in drawing, or if that number is in the drawing, in the first 5 numbers of that drawing, I want to print match and then increment my match counter. And I'm going to check each number. right? So if that number increments more than 1, I have 2 matches, I could have 2. And then it gets done checking and then checks the Powerball if that's true. If it is, I then call Powerball true, and then I print each one, okay? That's after this for loop is done. Once it goes to the next drawing, so let's go back up to this outer loop, I want to reset all that back to 0 and false so I can check the next number without introducing stuff from the previous drawing or the previous comparison. Does that make sense? Great, that's awesome. So now we know kind of how this is looping. It's doing one loop to get the drawing, and then doing an inner loop to compare the numbers, and then checking the Powerball, and then telling us what it saw, and then resetting those 2 variables because we want to have a clean result for the next drawing to check. So we're checking all the drawings in one go. We're not really, yeah, we're just building all the drawings that the user wants to check them all in one function, which is what we're doing here. But all we've done is print. We really haven't done anything to collect. We've just kind of printed it out into the console, and that's not really useful because we haven't saved it anywhere. Yeah, nesting for loops does. It takes a bit to understand. Just know that when you do nest them, this loop has to run completely before the next iteration of this outer loop. And because we have nested data structures in drawings, because it's a list of tuples, we have to do some sort of nesting if we want to compare the ticket to that tuple, which is a single drawing. Tuple to tuple, and they match size. So we've got it to print, and so now we kind of halfway hit this objective, which is the program should tally how many times the player hit a winning drawing. We're not really tallying, we're printing, and we don't know if it's a winning drawing yet because if it just matches one number, that's not a winning drawing. Now, one number plus Powerball is a winning drawing, but one number by itself is not. So we need to somehow save something to show like what we've won, or to show winning drawings. And I think what we should probably use is a dictionary to do that. Just so we can return like a kind of like a total, if you will, right? So so we can have this function do it this way, and then we can also go ahead and get our result and kind of do all the comparing in one. And I'll do that now, but when we go back, another day when we're fine-tuning this, I'm gonna change this function to do kind of ticket to drawing one time, not a collection of drawings, but we'll keep it this way for now and we'll fine-tune it later. So I want, instead of just printing stuff, I want to return something, right? So this function doesn't return anything, it just prints stuff out. So remember, return is an important part of a function in Python because that gives us a result to then do something else later on. Because we want to, just like the bank analogy, right? When you give the money to the bank, you want some sort of proof as a result showing that the money's in your account. Like, you don't just want to give the money to the bank. They're like, cool, thanks, bye. And you're like, no, give me like a receipt showing that my money is in my account and I can see my balance. Like, that's the whole point of putting it in a bank. So the same thing, when we do this compare, we're comparing all the drawings. We want to see something come out, like we want to see like a summary of all my drawings and what I hit as jackpots. And so we could build, like, before we do anything with a loop, we can kind of build a placeholder object, a dictionary that we can fill in. We could also build just an empty dictionary that our loop will fill in as needed. And we can introduce logic to kind of build those key value pairs. But I would say probably go ahead and just build a placeholder object for now that has all the combinations that we would need for a winning. So we need to build a dictionary that has basically this data. So we need to have a dictionary hold all of these. So basically like match 5 plus Powerball, match 5, match 4 plus Powerball, match 4, match 3 plus Powerball, match 3. We're not concerning ourselves with prizes right now. We're just going to use this to then have counters for each key that we can increment. The values for each counter we increment. Yep, 9 key value pairs. So a dictionary that contains 9 key value pairs. So this will take a bit of coding, but won't be too bad. So let's just say results. We can call it results equals, and we can open up a new dictionary. Right now, it's either a dictionary or a set because I haven't done anything, but I can go ahead and make that. So we can say first, match. Oh, we got to use what kind of data can be in keys for dictionaries? What kind of data is it limited to? Strings is 1. What other type of data can be a key?
Integer.
Integer can be a key. A tuple can be a key. Any immutable data type can be a key. Tuples really typically aren't a key, but you can use them like when you're counting like coordinates. Like if you have like coordinate pairs for doing some like geolocating stuff, you can have a coordinate and then how many times it happens. You could use that. But typically it's going to be either a string or integer. That's usually how I see them. And it's typically strings most often. So in this case, we could say match 5 plus PB. And then we put our colon and we say 0. And we do a comma. And then I can just do, and then in VS Code or other IDEs, I can hit Option Shift down and just build a bunch of them real quick. So that is 8, 9, and then I can say match 5, match 4, 4. We have match 3 plus Powerball, match 3. And then match 2 plus Powerball. And then match 2 plus Powerball. Match 1 plus Powerball. And then PB only. Okay. So I don't need this trailing comma. You can, it's either way, but okay, so that's our results. So now we have a dictionary with key value pairs, and each key is, it's going to match to a value. So basically, when I hit one of these scenarios with my loop, I want to increment this key by calling the appropriate key and then incrementing it. And where that could happen is at the end of every iteration of this matching. So after this if statement, I'm going to know what a match counter is, and I'm going to know if my Powerball is true or false. And I can use that. I can use in some sort of if statement, if you will, to look at that to put me in the right category here. If I have 3 matches and I hit the Powerball, I know I'm going to this key right here, and I'm going to increment that by 1. Does that make sense? I know for you folks, it's not intuitive, and this is a lot of new information being thrown at you. Close, Nika. That's close. So you don't just, there's a couple things wrong with that statement. You know, one, like Python is almost like English, but you have to do, if you're using like an and operator in between Boolean statements, you have to make complete Boolean statements on either side. So in this case, we could have an if statement if match counter equals, you know, if match counter equals 1 and Powerball, which the just putting Powerball will say a Boolean statement because if it exists as true, because if it doesn't exist, it would be false. So you could say if match counter equals 1 and Powerball, you can then have it do something, right? So we'll have to introduce a bunch of logic, but at least we can get it in here. So let's take this out and do this instead. So we're still here in drawing and drawings, but we got out of the second for loop and we have our, before we reset them, we're going to go ahead and do some stuff. So now we can, so we can just write a bunch of if else statements and kind of match each one of these, right? So if match counter five, so if match counter, yep, it would be a bunch of if and else if statements. Yep, you're right. That's how we're gonna write it this way first, and it's probably where we're gonna stop for the evening because we're already about 30 minutes left. But we'll be able to see it work. So, but we need to make sure we're doing this the right way. So right now we're gonna see if match equals 5. How could I only want to put this statement, like I want to have this statement. I just want to just check to see if match counter 5, because this covers 2 statements, right? We have match 5 plus Powerball. So I can do a nested if statement if Powerball, and I can do if Powerball equals true, or I can just say if Powerball. So if Powerball, then I would do results. How can I access that key? By doing the square bracket, match 5 plus PB plus equals 1. Else results match 5 plus equals 1. Okay, so here in this if statement, we've covered both of these situations. So inside of that if, so we're saying, hey, if this match count is 5, we already know we're going to win a lot of money. But then we just do some if statements, say if Powerball, then boom. Otherwise, just do match 5 because Powerball doesn't match. And we can just take this, then option shift down, down, and then we can change this to 4, 4, 4. I think we have 2, yeah, 3. Okay, so then, and then also with VS Code, you can also put your cursor in multiple locations by hitting Command and then clicking. And I can change them all to 3. And then I can actually make these else if, because if I hit the more restrictive one up here, I don't care about the other ones. So order matters. So I'm already doing this in the right way, but if I were to check for 1 first, right? Well, Well, see, no, because I'm actually checking a value, so it really wouldn't matter right now. So in this case, because I'm checking a specific value, it would still not hit. So in this case, right now we have if match counter is equal to 5, then I go into this logic for 5. If it matches 4, then I go into this logic for 4. 3, boom, and then I need to do something else here. So elif match counter equals 2. If match counter equals 2, and then I can do and Powerball, because having two numbers by themselves doesn't win you anything. So I have to have both. Then I can say results at the key of match 2 plus PB plus equals 1. And then what would my last two statements be? Anybody want to type them out? You just put it in the chat and I'll copy it over. Make sure you can see everything. So if match counter equals 1 and Powerball, okay. And then I want to add that. Match 1 and Powerball. And lastly, okay. So the last one is, I mean, yeah, you could really group 1 and Powerball and the Powerball together because you win the same amount of money. But we'll go ahead and just say elif Powerball. Yeah, I think at that point you have 0. That's the only other option you can have. Yeah, else you lose. Yeah, we can print that. You lose. So elif Powerball, and then it'll be results PB only. Better like next time, right? So else print no chicken dinner. There we go. So no winner chicken dinner. So you just no chicken dinner because you don't have winner. But let's get rid of this one because I don't care if we match numbers. I want to actually see a result. So now we have that at the end of everything. I can return. So see how this is getting pretty long now, right? So I make sure I'm on this line here. Out is this crazy long logic tree. Return results. That will return the results object that I've been changing with all this logic inside this loop. And then when I compare here, I can make it, I can just print it. I don't have to sign anything, print. I can just print that whole statement and I should hopefully get something back. Let's see. So let's do 100 drawings. I know we're limited to 10, but we can do 100 because I haven't limited it and it should work. Let's see. So here looks like I had Powerball only twice. I matched one plus Powerball here, and then matched 2 plus Powerball here. And then I didn't match anything else. Over 100 drawings. I just had a bunch of no chicken dinner. Maybe we shouldn't print no chicken dinner. Let's just get rid of that. We'll leave it like that. And let's do 1,000 times. We'll run this 1,000 times, see what happens. Okay, so I had PB only 39 times, match 1 plus Powerball 10 times, match 2 plus Powerball 1 time. Yeah, so that way your output's not crazy. The dot dot dot, the ellipsis is just it's a truncation of the output. It's just for ease of reading. You can expand it if you want to, but I didn't want to bother with that because I didn't want to see no chicken dinner a bunch of times. So I just got rid of the print statement. Let's go crazy. Let's run it 10,000 times. Hey, one time I had match 3 plus Powerball. Powerball only 296 times. Let's go crazy and do it 100,000 times. I matched 4 2 times. What was the prize for match 4? It was $100. So this was 10,000 drawings. Yeah. So 10,000 drawings. Each drawing costing $2. So that's $20,000. And over 20 years, you can only go through, I think they changed it to 3 drawings a week, but I think with 2 drawings a week, that's 4,000 something, like 4,096 drawings in 20 years. So you can do 20 years of drawings right now by just doing, let's say 4,000. That's 20 years of drawings that you could ever do. And I matched 3 5 times. That's $7. Spent $8,000. So what's the next logical step? So now we can, I think this is the results. If we look at this, the program should tally how many times a player hit a winning drawing. So we've done all that. Now we've returned something that is useful for some other further data analysis, like let's say how much money we spent, how much time we've taken to play the lottery. We can go on further down. So right now we have, just in these 2 functions, we have a way to compare the lottery reliably and see how many times we can win. Let's do 5 million drawings. So 5 million. This may take, I don't know. This may take a bit. It's running right now. I may have been a bit overzealous. We'll see. My fan's already on because of the video. So it keeps wanting to leave the stand. I need to get one of the M1 Max. This one's the Intel, and just the fan kicks on anytime I open Chrome. it would run much faster if I wasn't running a video, but for some reason the video takes a while. Oh, finally got it. Cool. All right, so 5 million drawings. I hit one match 5. Match 5 will get you $1 million. But I spent 2 million. Or no, I spent 10 million to play to win $1 million on one drawing. I matched 4 plus Powerball, which gives me 50,000 each. I don't know. This math isn't perfect. You know, the math I'm doing now is slightly off because I'm not removing a number and then like reshuffling. So there is a bit of a difference. I could fine tune if I want to, but I mean this is a fairly close approximation, right? Because I have to get 5 unique numbers. But yeah, you can see you get a lot of the matching one plus Powerball. It happens quite a bit, right? But the odds just are not in your favor. So what do y'all think so far of this lottery generator that we've done? Does that help you see how we can use data types, manipulating data types? You know, thinking about the small things like the user input, right? The user input, you know, we didn't know that it was actually it was a string. We have to cast that to an integer, otherwise it wouldn't work. It would give us an error. And so you'll get those error messages all the time. And you know, if you're testing your code, it's good to kind of test the section, do print statements wherever you need to kind of see how the results you're going to get. Use your type function to see what type of data you're working with, so you know what you're working with and what expected results you're going to get back. I think we've covered all the data types. We had string, we cast it. We're printing strings. We're using strings in our keys. We're accessing key value pairs, and we're changing the values with our using the key with the results. We have this long chained if, else if like statements to kind of make sure we hit every possibility of the lottery to put it in. We're checking to see if Booleans are true or false, and then going to branch logic based on that. You know, here we're saying if it's true here, if it's not, do this. We're calling functions, calling several functions. We're using them to build, we're reusing functions to do two similar but different things, right? This logic applies to the drawing. It applies to the ticket. So why not reuse it? Just make it a random generator and then just name your variable the result of that function. And then we're kind of getting our final result by calling this big function that does everything, right? So maybe we can break up the logic here into smaller functions if we need to. Right now, it's fine. It runs, but it's quite wordy and quite big. This logic tree, you know, could possibly be improved. We can see maybe in another session, but you know, I think we've hit a lot of things that we need to know how to do. And I hope that this, going through this thought exercise and this process of building something that's probably way more complicated than looking at, right, will help you see how you can break down each step. And that's really my goal. My goal is to see you break down those steps into those small pieces, those small chunks, to build up the your skills with problem solving and breaking the problem down, the abstracting, the finding results of small problems to answer the bigger ones. And it's a marathon. It's not quick. It's very slow. And of course, you know, coming up with something like this on your own right now is probably not realistic. But you know, at least seeing this process helps maybe open your mind to, you know, trying different things. And that's really what I wanted to do with this exercise. So that's really it for the lesson today, because we're already at 8:46. So we have about 15 minutes left. Are there any questions for me? Anything that you would like to see maybe in a different way with accessing data types, you know, manipulating data, using for loops, functions, anything really? I'll be happy to kind of go over any of these concepts.
I have a question, but could you just go over maybe the what it looks like for a nested for loop again? Um, I'm using them a lot, and like I'm trying to do certain things, and like right now, I'm trying to figure out like say I had like a string, I'm trying to find out like every combination of that string and put it into like an output. Like, and this is for like not necessarily the same thing as like the coding challenges, but like that's sort of some partial logic to a part of the problem. And I'm trying to use a nested for loop to sort of do that, and it's giving me like I think my gap of understanding is when it comes into like the nested for loop.
Okay. So like let's say you're trying to let's just say we have a string. So let's say my string equals A, B, C, D. And we want to print out every combination of letters, like every pair combination, if you will. So we could say result equals result equals empty list, and then for letter, or let's say for one letter, let's do first in my string for second in my string result dot append. In fact, I'll have to do something else. So let's do it this way, actually. So for I in range my string, for J in range my string, or no, range I plus 1. That'd be I plus 1. Boom. Let's do range len my string. And then for J, so what I'm doing is I'm building what I want to do is I want to just append each pair, right? And so I want to loop over with the outer loop, I want to start at A, and then with the inner loop, I want to start at the one that's above, and then I want to make that inner loop run to the end. Then I is going to increment up 1, so I'm going to go up to B. I don't want to start the first loop at A because I already have that combination. So I want to start it actually at whatever it is plus 1, right? So it'll be my, let's see, range. It'd be I plus 1. We'll try this first. Results append my string. It'd actually be a, I'm gonna do a my string I, comma, my string J. And so what's going to happen here, I want to make sure I have this right. And, I haven't solved these kind of things in a while, so I need to make sure I'm doing it right. So for I in range length, my string, so that's going to be the stop here. So it's going to go up to, but not including this, the length, which is 4. So it's going to stop at 3, which is luckily the last index in there. Then I want to loop with this one. I want to increase the index. But I think for this one, I actually need to have I need to have a stop. So the start is going to be, it's going to be length my string -1, and I'll explain why in a minute. Because I want to stop at the letter that's right before the end, because I'm going to get that last combination with this J. Because it's going to get A, B, and then A, C, and then A, D, and then it's going to go up 1. And it's going to get B, C, B, D. It's going to get the C, and you get C, D, and stop. I don't want it to go all the way to the D, because the D doesn't combine with anything else that hasn't already been combined. And so then for I in range, and that's going to be, or for J in range, and it's going to give me whatever this is +1. So I don't want that. I want, what do I want that stop to be? I want it to be the end of the count. So it's going to be a start of I +1, and the stop is going to be len the stop is going to be the length of my string. Oh my gosh, what did I do? Oh, I just scrolled up. And so that will take me up to, but not including, so the last one. And so whenever I'm at the last one, it shouldn't, I think it'll work. Let's see. Let's see what happens. And play. It didn't fault out, so that's good. Let's go ahead and print result right here. AB, AC, AD, BC, BD, CD. Yep. And so let's do A, B, C, D, E, F, G, H, H, I, J. A, B, A, C, D, A, D, A, E, F, G, H, I, J, B, C, B, D, and it goes all the way down the end. I, J. Does that make sense what I did there?
Some parts, yes. Other parts, like the I+1, and then, yeah, the
So
length of
remember,
the string.
so the range is only going to take integers as its values. So both of these are integers, and same with this. This is an integer. So what this is, so for I in range, the length of my string -1 is this length right here, which right now is 11. 1, 2, 3, 4, 5, no, 10. So it's 10. And I want to do it actually up to 9. So I'm saying for I in range, so I'm going to run this outer loop 9 times. And I I then, for each iteration of this loop, I would run this one. And I'm saying, hey, I want to start at whatever I is +1. So I don't want to hit the A again. With the first time this iterates, I don't want to hit this A again. I want to hit the B. So I'm starting at B, and then I'm going all the way to the end because I want to hit this last letter. So I'm not doing the -1. I'm going all the way to the end, which is the length of my string, which is 10. I want to go up to, but not including 10, because I want to hit the ninth index, which is starts at 0 up to 9. J is my string at the index of 9. So I want to start at whatever this outer loop is and go up to, but not including 10, which is 9. And then I just want to append the result of my string at the index of I and my string at the index of J, because J is going to increment up as well. And then it's going to finish the increment. This will increment once, and then this will go through the whole thing starting at I +1. So when I is B, I'm going to start at C, and I'm going to go to the end. When I is D, I want to start at E and go up. So as far as every combination, I want to let you guys flex your thoughts on that one, but I think this will get you a good starting point, because right now you're getting every combination of 2 letters. So I want to maybe let you flex your thinking on that one for a bit. I mean, we're coming back tomorrow. We're going to continue on with this lottery. We may even get done with this lottery when else I think of something else to do. But we'll be doing other stuff. So you were thinking more nested loops?
And enumeration, nested loops and enumeration throw me for a loop.
Yeah, enumeration is just all you're doing is you're just getting an index and the value. So if I were to enumerate over my string, I would say for index comma value in enumerate my string, whenever it printed out, it'll print 0A, 1B, 2C. It'll just give me the index, and then I can use that in the loop to do something. Whereas I can build off of that, I can then search for, I can search for wherever the letter D is. If there's multiple Ds, I can get all the indexes of where that lies, and I can do something with it. So enumerate, if you want to see that really quick, I can print that out. I know we're coming close on time, but I can do that real quick. So let's write for index comma value in enumerate my string, print. I think I did this exact example. This is the index. Index. This is the value. Value. And if I run that, this is the index, this is the value A. So 0A, 1B, 2C, 3D, every time it iterates. Yep. Relying on lists is normal, because lists are comfortable. They're unordered, but they keep the same, or they're ordered because they keep the same order when you put stuff in. So you can kind of mentally keep track of that a little easier. So yeah, relying on lists right now is fine, and that's good, because you're sticking one. If it doesn't really fit, you're forcing to fit. But sometimes other data types are more useful. So maybe consider exploring dictionaries. You'll find that dictionaries end up being a little more powerful. I tend to lean towards dictionaries more than lists now. So as you just get more practice, I think you'll do fine. So Yeah, thanks for coming along with me on this ride through the Big O notation and kind of go over that last lesson there. And then really we kind of just dove into just really messing with that lottery and those data types. And that was I think that was pretty awesome. So hopefully you guys got some good stuff out of it. And we will see you tomorrow.